right. Hi, everyone. Good morning. I'll now give my talk on our new algorithms to improve streaming approximation for Max-DICUT by some local snapshot computations in the streaming model. And the talk is going to be on based on joint works with Raghuvansh Saxena, Noah Singer, and Madhu here. Okay, so I'll first begin with some definitions. In the Max-DICUT problem, you have an undirected graph, and your goal is to find a bipartition that maximizes the number of edges that go across. And this is what we call the cut size, or the max cut size of the graph. And our goal is to output the largest cut size. We don't even care about the partition, it's just the size of the cut that we want to output. The max-directed cut, or the Max-DICUT problem, is a related problem where you have a directed graph, this time instead of undirected graph. And again, you're interested in a bipartition. But now you only count the edges that go in one direction. Let's say, in this case, just the forward edges, all marked in green, and that's the die-cut size. And again, the goal is to output the largest die-cut size. What's a streaming? How is this problem framed in the streaming setting? You just have these edges stream one by one very quickly, and then you have very little space. You can't store the entire graph, and in this limited space, you want to compute the size of the largest cut or die-cut. Of course, this problem is NP hard, so what we're really interested in is approximation algorithms for this. And an alpha approximation algorithm basically just output a value that's just at least alpha times the optimum and at most the optimum. Okay, this is the model. Now, what are some of the folklore approximations for these problems? So first thing is actually, you can get arbitrarily good constant approximation in O tilde n space. This is by just sample order n over epsilon square random edges, just compute the max cut, max die-cut value of whatever you sample. And this could take exponential time, but again, we are not limited in time, we're only limited in space, okay? And this gets us 1 minus epsilon approximation. Now, so really the main question in streaming model is like, what approximations are possible for these problems in little o of n space? Now, you do have trivial approximation in just log n space. Basically, these are based on random approximations for this problem. If you take max cut, you always have a cut that has size at least m over 2. So you simply count the number of edges and output m over 2. That gives you half approximation. Similarly, for max die-cut, you can get 1/4. So the real question is like, can you beat these sort of random approximations in little o of n space? Now, let me very quickly highlight some results about these max cut and max die-cut problems. Max cut is actually a very central problem for proving lower bounds. It was shown by, in a breakthrough result by Capital-O'Crutchon that this problem does not have any non-trivial approximation in little o of n space. You can do half very trivially, and if you want to beat half, you can go all the way to 1 minus epsilon in n space, and there's sort of nothing in between. And I call it a central problem because these techniques are nicely extendable to even other CSPs, and that's what we showed in a later work. Now, the Max-DICUT problem, for a very similar reason, is actually a central problem for algorithms, because more often than not, whatever algorithms we develop for Max-DICUT can also be extended to other bigger class of problems called CSPs. So the first work in this line of research for Max-DICUT was in a joint work with Venkat and Amaya, where we gave something called a bias-based algorithm, which non-trivially approximates this Max-DICUT problem in log n space. And in a later work with Chining and Sasha, we actually showed that this algorithm is optimal. If you want to beat it, you need at least square root of n space. And very nicely, in a further joint work with Madhu, we showed that this result can be extended to all CSPs, and we gave a full dichotomy characterization. Now, what are the goals of my talk? I will first show you, this is a result based on joint work with Raghuvansh, Noah, and Madhu, where we beat this bias-based algorithm, which was optimal in little o of root n space, using just slightly more than square root of n space. So that's the first work that I'll talk about. And the second is an upcoming work with the same authors, where we show that you can go all the way to half approximation for Max-DICUT in little o of n space for bounded degree graphs. And this factor is actually optimal. The reason is because we already know that for Max-CUT, you cannot beat half approximation in little o of n space. Through a simple reduction, you can also show that that lower bound extends to Max-DICUT as well. You cannot beat half approximation for Max-DICUT in little o of n space. And not just that, the hard instances that you have are actually bounded degree graphs. So in that sense, this new algorithm that we have is actually optimal. And the key sort of contribution underlying both of these works is that we show how you can simulate certain local algorithms for Max-DICUT in the streaming setting by capturing what we call local snapshots of the graph. So soon I'll talk about what these local algorithms are and also show how to compute local snapshots that help you simulate these local algorithms in the streaming model. Okay. First local algorithm that we'll be focusing on is called oblivious algorithms. This notion was introduced by Feige and Joseph in 2015. What is an oblivious algorithm? So before that, I need to define this notion called the bias of a vertex. Bias of a vertex, which sort of prominently appears in all our works, is defined as follows. It's just the ratio of the out degree minus in degree to the total degree of the vertex. Observe that this is a quantity between -1 and 1. Now, oblivious algorithm is the following algorithm, where it's going to randomly assign every vertex. So basically, it's going to say this vertex belongs to left set with some probability and right set with some probability. And this probability is going to be only a function of its bias. So if you have some vertices of the same bias, you're allowed to randomly assign them all with the same probability. That's the constraint of an oblivious algorithm. Okay, and in that sense, it's local because when you want to assign a vertex, all you're going to do is just look at what its neighbors are, how many of them are outgoing edges, how many are incoming edges, and that's the information you're going to use to determine what the random assignment is. So that's the oblivious algorithm. And now the approximation ratio of this oblivious algorithm is just the expected value of the die-cut it produces to the, question? Okay. So the ratio is just like the expected die-cut value to the true optimum. Now, okay, what are known oblivious approximations for Max-DICUT? So Feige and Joseph, in the same paper where they introduced this notion of oblivious algorithm, showed that you can get oblivious algorithms for Max-DICUT that has at least 0.483 approximation. And this is in contrast to like our best little of root and space streaming approximation for Max-DICUT, which is only 0.44. So the first question is like, okay, can we implement these oblivious algorithms in like more than little of root n space, but less than n space, thus obtaining better approximations than what we already know? And that's what we show in this work. Okay, that it is possible using just O tilde root n space, you can implement any oblivious algorithm, and essentially that helps you get 0.483 approximation.
So the 0.44 is optimal for little of square root n?
Yes, that's correct.
A way to understand this constant?
So that's a great question. Okay, but as a rational number, it's 4/9. I'm sure that still doesn't make any sense. Yeah, I don't know if there's a very nice way to describe it. It's just like, so this, what happens is there's a notion you can define called the bias of the graph itself. And it turns out that if two instances have different biases, then you can separate them. And it's also the case that for every value of bias, you can construct two instances that are inseparable also. And so that's sort of like the dichotomy about bias. And this 4/9 is like the tightest gap you get between like how much you can push. Like I give you a particular value of a bias. You're trying to create two instances, one with the largest Max-DICUT value as possible, one with the least Max-DICUT value as possible, so that you get the best gap. And that's 4/9. That's a good thing I can give, but I don't know if there's any intuition for the numbers themselves, but that's a very good question. Thank you. All right, so this is the thing that we want to do. So how do we do the streaming implementation? The nice thing about this Feige-Joseph algorithm, it actually only has a constant number of bias classes. Like, of course, like you have like infinitely many real numbers between -1 to 1, but it's not just gonna like look at all of that. Instead, it's like step function sort of thing. It only has a constant number of bias classes where it partitions this entire range -1 to 1 into some like constant many classes and says that, let's say your bias fits in like the first class, then with probability P0, I'm going to put you in the left set, and with 1 minus P0, you're going to be in the right set. So that kind of a thing that you only care about like these finite classes. What this means is that, so now I want to compute, so in order to get a 0.483 approximation, I need to just compute the expected die-cut value output by this oblivious algorithm. And in order to do this, it actually suffices to compute a constant size snapshot of the graph. And what is this? Just collapse vertices within the same bias interval into like a super blob or something. And this is sufficient because, so how do you output this like expected die-cut value? You want to compute for every edge, what is the expected probability that this edge belongs to the die-cut? That is only a function of the rounding probabilities for the endpoints, which in turn only depends on which bias intervals they belong to. So all you really need is just like compute your bias intervals and then look at the number of edges that go from one bias interval to another. That's all the information you need to compute the expected die-cut value. Okay. All right. So now our entire goal boils down to like computing this snapshot of the graph, which is just a constant size object. Yeah.
Not just the size, but the actual partition of vertices is also being computed in this algorithm, right?
That's a good question. So the thing is, like, because it's like just a square root of n space algorithm, you don't even have enough information to store something about each vertex. So it's not like exactly it will give you what the vertex is, but you can think about it this way. So it's like the local algorithm already tells you, like, you give a vertex, I will tell you with what what the assignments are. That's already determined by the algorithm itself. But here we are just trying to compute the expected die-cut value of the algorithm in the streaming model.
Okay. And isn't it possible, like, since this is a streaming model, you just output once you've determined which side the vertex and the cut is?
So that's a good point, but it's like, as I said, like you cannot store you cannot store the entire biases of all the vertices. So if let's say you can and you have that space, then, or even further, like let's say you just want for one vertex, you already have some target vertices, you tell me beforehand, then easily I can just like, all I need to do in the streaming model is just compute the biases of the vertices, and then the oblivious algorithm tells me how I'm supposed to round them. But now the thing that I'm trying to do is like compute this global information about the graph, which is the expected die-cut value. But at the same time, I don't have enough space to store information about each vertex. Another question?
I'm sorry. Can you just remind us what bias intervals are?
Oh, yeah, sure. So bias intervals is just that, so what they do is like, let's say that I'm looking at like a 3-interval algorithm or something. And let's say these pivots are like minus half, half, or something like that. Let's say there are only 2 pivots. So the bias intervals are like -1 to -half to half, half to 1, let's say. Now the bias itself, if you recall the definition, it was like out degree minus in degree divided by degree. So what this algorithm does is that for every vertex, you just compute the bias, see which interval it belongs to, and then it decides how it should round. That's all it cares. It doesn't really care about the global structure of the graph, nothing. All it cares is just what the bias of the vertex is, which interval it belongs to. These are rounding probabilities. When I say rounding, it's like we are looking at a randomized algorithm, which is going to produce a die-cut. And whenever you want a directed cut, you have to talk about a left set and a right set. And this rounding probability just tells you like what's the probability with which you're going to place a vertex in the left set versus right set. That's only a function of the bias.
But technically, any part of the graph can be the same bias interval, right? You take this big graph, the bottom is middle.
Yes.
Like 2 vertices which are on the opposite sides.
Oh, yeah.
Could technically have the same bias. So I'm just thinking if you collapse them both into the same. So the collapsing process does not depend on where it is in the graph, or
oh yeah. So I'm not really thinking of an embedding or anything like that. So it like the spatial locations don't really matter. It's like when I say collapse, it's just like put these 2 vertices together, and whatever the outgoing edges are. So sort of like, let's say I collapse 2 vertices, all the incoming and the outgoing edges, also instead of going to the individual vertices, now everything goes to this super blob that I just created. So if you collapse 2 vertices here, they're going to be in this blob, and all the incoming edges are going to be like represented here, and all the outgoing edges are also represented.
Contraction.
Yeah, it's like a contraction. Yeah, maybe that's a better word than collapse. Contraction of vertices. Yeah.
Thank you so much.
Thank you.
So in this blob, there are like R or R plus 1 super vertices.
Yes, there are R plus 1 intervals here, or R. Yeah, yeah. So yeah, exactly. So there are R super vertices, and each corresponds to a bias interval. And all you're measuring is how many edges go from like one blob to another, and including self-loops. All right. So now I'll show how we compute these snapshots. First, I'll talk about some special cases. Let's say the edges are actually randomly ordered. In the stream, you have like randomly ordered edges. Then you can simply take the first constant many edges. This is like a random sample of the edges of the graph. You store the induced subgraph, track the biases of the vertices, and that gives you a snapshot, and just compute snapshot from that. It turns out that this actually gives you a very good approximation. In fact, you get like 1 minus epsilon approximation for the true snapshot. And you can also prove concentration using things like Chernoff bonds. And in fact, this is only order, log, and space because, yeah, you only look at these edges, and that's all you care about. Now, what happens for bounded degree graphs? So for bounded degree graphs, you can do something very similar. Instead of like sampling constant random edges, you rather sample like order square root of n random vertices and store the induced subgraph, again track the biases and compute the snapshot. These edges, like the induced subgraph edges that you store, they're not actually independent. So you wouldn't get like Chernoff bounds like here, but then again, like the variance is limited because these graphs are bounded degree. So one edge is not going to depend on, it's going to at most depend on the other edges. So you can show that for this process also the variance is bounded and use something like Chebyshev to compute the snapshot. But the thing is like the bounded degree assumption is like really crucial here because let's say I have this star graph where you have like one vertex and you have like, it's connected to like order n vertices. Now, when I sample square root of n random vertices, with high probability, they are going to be these outer vertices and not the inner vertex. And really what you see is like there's not even an induced subgraph, so you get absolutely no information about what your graph is. So that's why for these sort of simple algorithm to work, you really need bounded degree assumption. Now I'll show you what we actually do for more general graphs, how we compute these sort of snapshots. The first idea is that we do a layered sampling of vertices. Like if a vertex is really high degree, like the star graph, you really need that vertex to be present in your sample. And if a vertex is really small, then you can like do this whatever square root of n vertex sampling or something. So first we do a partition of the degrees of the degrees. Basically, like the degree can range from 1 to n, and you can sort of get log n partitions of the degrees. And our goal is to like, if you look at this interval between d over 2 and d, roughly we want to sample vertices with probability at least d over square root of n. Notice that this is still only square root of n space because like you have roughly n over d vertices in this interval. And if you're sampling them with probability d over square root of n, you roughly get square root of n vertices in each interval. Okay? But the issue is that you do not know the degree of the vertex when it first appears. When I say you want to sample a vertex of this degree with this probability, you're not going to be able to do it right away because in the streaming, we have these edges that come in the stream. Just by looking at a vertex, you're not going to be able to tell what the degree is. So that's the first issue. So how do we handle it? We actually do a layered sampling of edges, and after that, do the sampling of vertices. So what is the sampling of edges? You just roughly subsample edges with probability, let's say 1 over d. And observe that if your vertex has degree d, in this new subsampling, like once you do this, you'll have like constant, these vertices will be roughly of constant degree. So that's the idea. So you subsample edges with this probability, and in the resulting subsample graph, you look at all the constant degree vertices. Those are roughly your degree d vertices. And then you'll further subsample those vertices with the probability that you desired and store the induced subgraph. And yeah, that sort of is the idea. Now, what is the issue? So you can do all this process. So roughly for each degree interval, you first subsample edges, look at the constant degree vertices, and then further subsample them and store all the edges incident to it. Now, the problem is that, let's say your vertex is in the border. Let's say it's degree d over 2. Then you could, with very high probability, classify it either in the interval, d over 4. Yes. So if you recall, we had these bias intervals where the pivots were differing by a factor half or something. And if your vertex has degree somewhere in the border, you could misclassify it. And this is true even about the bias. When you're computing bias, if your bias, let's say the pivot is like b sub r or something, and your vertex also has exactly bias b, if you're not able to compute it correctly, then any mistake could put it in different bias intervals, so you're not going to get exact computation. So this is how we handle that issue. So first of all, the snapshot that we now want to compute is this question. Originally, our question was like, how many edges go from some bias interval bi to some bias interval bk? Now we also have a refinement where you also put in the degree intervals. Like, so you have a bias interval, degree interval, and you ask how many edges go from this bias interval, degree interval to another bias interval, degree interval. And so what we do is that instead of like this snapshot, as I mentioned earlier, it's going to be really hard to compute this correctly with high probability, because when you're looking at the string and trying to measure which vertex belongs to what degree interval or bias interval, especially at the boundary vertices, you're going to make some mistakes. So you won't be able to compute the refined snapshot with high probability. Instead, we compute something called a smooth snapshot, where we actually try to compute the average of this snapshot over like a window of size W. This basically like gives you this sort of window of error where if you misclassify your bias or the degree interval within some window, then you're still fine because you're only trying to compute the average over a particular window size. Okay, so obviously when I'm looking at this kind of smooth snapshot, if you're going to increase your window size, let's say my window size is like this whole dimension of this refined snapshot, obviously that's very easy to compute. So if you're going to increase the window size, you're going to get better estimates. But the caveat is that it's not going to give you enough information to figure out what your even original snapshot was, because this is still our goal. We know that we can't compute it accurately, but we still want to retrieve it somehow. So we need to kind of balance between larger windows versus smaller windows. Okay, so that's the point I want to make now. So why don't these kind of misclassification errors don't matter? First of all, observe that degree misclassification errors do not affect the final snapshot that we want to compute, because all we want to do for the algorithm itself, like if you recall the oblivious algorithm, that does not care about what the degree of the vertex is. All it cares is only about the bias of the vertex. So in that refined snapshot that I defined earlier, even if I misclassify the degrees of the vertices, it's not going to really affect my final snapshot computation, because like all I care is only the biases of the vertices. And yes, that's the. On the other hand, if there is no bias computation, this is what I was trying to say. If there's no bias computation, error in bias computation and error only in degrees, then we are fine. But what happens if you have bias misclassification errors? As long as these errors are within only plus minus epsilon. Say, let's say like originally the oblivious algorithm of Feige-Joseph had only like C intervals or something. You can blow up these intervals so that within each interval, the biases vary only by like a factor epsilon or something. This is still like only constant many intervals. But what that shows is that if you look at many close enough intervals, then if you misclassify bias, that's not going to change the Max-DICUT value much. This is because, let's say that you misclassify a particular vertex, you can still perturb the original graph to get a new graph with a similar Max-DICUT value, and the smooth snapshot of the graph matches the defined snapshot. What do I mean by this? So let's say you misclassify a vertex V, and let's say its bias is now off by epsilon. You can create a new graph where you create a new vertex and modify the bias of this vertex by creating at most epsilon d new edges. So this does not change the Max-DICUT value of your new graph. So this is like a reduction where even if you misclassify biases, you can get a new graph where the bias profile matches that of the new graph, and the Max-DICUT values of the two graphs don't differ much. Sorry if that's a mouthful, but I hope at least the high-level structure is sort of clear. All right. So that's sort of about the first local algorithm, where we talked about an oblivious algorithm and how to implement it in streaming in square root of n space to get better than 0.44, or in this case, 0.483 approximation. Now, for the second half of my talk, I'll talk about this local algorithm, which is actually a distributed algorithm, and show how to get half approximation for Max-DICUT in the streaming model. Okay. So distributed algorithm, if you haven't seen before, this is like a message passing model where you have like all these vertices of the graph, which are passing messages in each round. In every round, a vertex is allowed to receive a message from each of its neighbors. And after k rounds, each vertex, based on all the messages it receives from these neighbors in these progressive rounds, it can decide what its assignment is. That's sort of the idea of a local or distributed algorithm for Max-DICUT. And this work of Sensor, Hillel, Levy, Shachnai from 2017, which indeed is actually an extension of this greedy approach of Bookbinder, Feldman, Sefi, and Schwartz, gives a distributed algorithm for Max-DICUT that gets a half approximation using only delta plus 1 rounds of communication. And this algorithm is going to be the framework that we use and implement in the streaming model. Okay. Is the model clear? The distributed algorithms message passing model? Okay. Okay. So what is this distributed algorithm? I'll give a very sort of high-level sketch of this algorithm. So first step, so delta is actually the max degree of the vertices. Sorry, I should have mentioned it in the previous slide. So if your max degree is delta, there exists a delta plus 1 vertex coloring of the graph. And in the first step, they actually obtain a delta plus 1 vertex coloring. And then the idea is to assign sort of these vertices in batches. So let's say they label the color from 1 to delta plus 1. In the first round, they assign vertices, all of this color 1 vertices. This is not going to depend on any of the messages or something. And in the second round, you use like messages from these color 1 vertices, or what the assignments are, to assign vertices of color 2, and so on. So after every round, at every round after a vertex is assigned, it sends a message to all the higher color neighbors. So in that sense, because you only have like delta plus 1 colors, you have delta plus 1 batches and totally delta plus 1 rounds of communication, and that's how this distributed algorithm works. And this is like a randomized algorithm where whenever you assign these vertices, it's a random process, and with some probability you assign these vertices. And so the approximation ratio is defined as the expected DICUT value produced by this distributed algorithm to the optimum. And they show that this is a half approximation. Unfortunately, I wouldn't have time to go into further details on how these algorithms work, why it has approximation and stuff, but yes. So first you did the coloring, and now you're trying to get a die-cut partition. So each time the assignment is again 0, 1, but it's going to be a probabilistic assignment, whether you're on the left side or the right side. And then it sort of proceeds in rounds. You first assign one batch, that batch sends some messages upwards, and then the next color gets assigned, and so on. And you have like delta plus 1 rounds.
Probability just depend on how many neighbors, or of course, so far.
That's a very good question. Yes, that's a really good question, and it's true. For the very first color, all that will matter is only like the bias information or something. How many outgoing neighbors are there? How many incoming neighbors are there? That's going to determine what its assignment is. But for the next color, it's sort of, you do one up. Like, okay, what were the assignments for my neighbors? And of course, what are my out degree, in degree, and something like that. You sort of put all that information together and then get the color 2 assignment. And then the color 3, all these messages from downward, plus your own degree information to get, and so on. So this is,
yeah. What is the randomization again? Sorry, is it just
yeah. So I didn't explain it very clearly. So it's not a deterministic function. So you get some messages, and you know like what your own out degree and in degree is. And the assignment is going to be like a probabilistic function, not a deterministic function of all this stuff. But I'm not going to go into the mechanics of exactly how it's assigned, but it's a probabilistic function. Any other questions?
And this vertex coloring is computed without achieving the directions of the
this vertex coloring, yes, this one actually ignores all the directions and stuff. It's just like the underlying undirected graph must be a proper coloring. And in fact, they even use a distributed algorithm to first do this vertex coloring. With I think that can be obtained in like log star delta rounds or something like that. Anyhow, so yeah, very good questions. Thank you. So yeah, the vertex coloring, when we say proper vertex coloring, it's only the directions don't matter. It's just like the underlying undirected graph should be properly colored. So this is the distributed algorithm. Now, how do we do the streaming implementation? First of all, we want to reduce the radius. Like we do not really want like delta to be like the number of rounds, because that's going to be really problematic for us in the streaming model. So first we do this random coloring. Just use order 1 over square root of epsilon and randomly color a graph. You're going to have some monochromatic edges, but you're not going to have too many monochromatic edges. It's just epsilon fraction of the edges are going to be monochromatic because you're using order 1 over square root of epsilon colors. Just delete those edges, like ignore those edges, forget about them. Your Max-DICUT value is not going to change by more than epsilon. That's all you're losing. So you can think about this as like a distributed algorithm that gets half minus epsilon approximation in order 1 over square root of epsilon rounds. And really, we are going to only get this half minus epsilon approximation in the streaming model, and that's going to be our goal. Okay. So now we want to compute this expected DICUT value output by the distributed algorithm. And this is again very similar to like the obvious algorithm where you, Yes, you sample like order 1 random edges, and for each edge you want to compute what is its probability that it belongs to this like DICUT partition, and that helps you compute what the expected DICUT value is. Okay, so really the crucial thing is like this probability of belonging to this DICUT partition output by the distributed algorithm. That's what we are trying to compute. In the obvious algorithm case, that probability was only a function of the biases. Now it's going to be a function of like the neighborhood of the edges. That's sort of what the distributed algorithm uses. That's what we are going to see now. So we have this notion of radius k neighborhood of an edge, which is just that you can define it very naturally by a BFS search. This is a radius 1 neighborhood. You take all the neighbors. And then radius 2 neighborhood is just take the neighbors of the neighbors. That gives you radius 2 neighborhood and so on. Notice that I'm not putting any directions because as Shagnik pointed out earlier, for the distributed algorithm itself, we sort of, at this point, we don't really need the directions or something when defining neighborhoods or even the coloring. This is what we call the radius neighborhood of an edge. And so what I'm going to show is that it suffices to just look at the radius 1 over square root of epsilon neighborhood of that edge. Basically, how many ever rounds of the distributed algorithm you have, that is all you need to really compute the probability that that edge belongs to the DICUT output by the distributed algorithm. Why is that the case? Look, this is a valid 3 coloring of this neighborhood that we see here. Okay, let's say that for in this coloring, like red is given more priority than blue than green. What this means is that the distributed algorithm first processes green, like this color 1, let's say color 1 is green, color 2 is blue, color 3 is red. So green is first processed. Then you sort of send those messages to blue and red vertices, and then the blue vertices are processed. Again, the messages are passed, and then the red vertices are processed. Let's say that is how the distributed algorithm works. These arrows indicate like how the messages are passed. Basically, green passes to blue, blue passes to red, again, green passes to red. Any lower color vertex is going to pass messages to its higher color neighbors. Now, we want to compute the probability that this particular edge belongs to the DICUT partition output by the distributed algorithm. Note that the messages that really matter are those that go upwards, in the sense that let's say we want to compute the assignment probability for this red vertex. That's going to depend on messages it receives from its immediate neighbors. And they, in turn, only care about the messages they receive from their neighbors and so on. If you look at these edges that are not marked orange, these edges or these messages are never going to affect what the assignment probability is for this red vertex. What that means is that the paths, the message paths that you care about for every vertex is going to be at most the number of colors. The length of that path only is going to be at most that color because messages are always passed from lower color to higher color. And your path length cannot be more than the total number of colors itself. And only these paths matter for your own assignment. And that's why this radius neighbor, you could potentially have much longer paths which are all valid colorings, but if you only want to consider paths that with arrows going upwards, those paths have length at most 1 over square root of epsilon. And that's why to compute the probability that an edge belongs to the DICUT, or in other words, what is the probability for each endpoint to belong to this DICUT output by the distributed algorithm, you only need to look at this radius 1 over square root of epsilon neighborhood, and with that you will cover all the paths that really matter for this probability computation. This is a little subtle, but if you have any questions, I'm happy to answer. Okay. All right. Okay, now that we have this sorted out, we define the type of an edge to be just its radius 1 over square root of epsilon neighborhood. For bounded degree graphs, where you have an upper bound on the max degree, you only have a constant many possible types. And our goal is to estimate just this type distribution, because as I argued before, all that matters is the radius 1 over epsilon neighborhood. We can think about it as a type of an edge. And once you have the radius 1 over epsilon neighborhood, you know exactly what the probability of that edge being in the die-cut is. So you sort of only need this type distribution, and this type distribution itself is only supported on like constant many objects. Okay. So sublinear space, our algorithm is the following. So for each type T, we do the following. We sample a bunch of random vertices, which is exactly sort of similar to our previous algorithm that I mentioned. You again store the induced subgraph and also the degrees of all these vertices. And then you only consider those edges whose entire radius neighborhood is contained within the store graph. As long as you sample enough vertices, you can make sure that you at least have, like for each type, some constant number of such edges whose entire neighborhood is within this stored graph. Then you compute the number of edges of that type and appropriately rescale based on what the probabilities are and stuff like that. But at least the high-level idea is just sort of very similar. Again, here you will have some kind of dependence between edges. You're not going to have perfect independence, but because they are bounded degree graphs, again, the variance is going to be bounded. You use something like Chebyshev to show concentration. Okay. Now, that's the sublinear space setting. What about the random ordering? Again, we have log n space approximation. And this algorithm is actually heavily inspired by a prior work of Monamezadeh, Muthukrishnan, Peng, and Solar. And the high-level idea is just that, so we have constant random edges, which is the first edges in the stream. We sort of want to find out what the types of these edges are and estimate the distribution from that. But the problem is that, let's say I want to do this BFS search and determine what the type of an edge is. Because of the way streaming algorithm is, the type you see may not be the true type. Let me explain it. Let's say this is an edge, and let's say this is how its neighborhood looks like. And you want to estimate and find this neighborhood. But what you may find in the streaming may not be something like that. For example, let's say these numbers denote the order in which these edges actually appear in the stream. First, you have this red edge, which is the edge for which you want to compute the neighborhood. Then you have a second edge, third edge, fourth edge, fifth edge, sixth edge, and so on. Now you see this first edge in the stream. You see this edge, but when you see this edge, you actually have no idea it belongs to the neighborhood of that edge. So you can't really store it. You ignore it. You see this edge. Yes, you store it because it's like the immediate neighbor of that. You see this, and you see this. And that's all. This is what is your visible type from the stream, though this is your true type. And it turns out that by looking at this visible type distribution, you can actually compute the true type distribution. That is what you want to compute the die-cut value. So in other words, the visible type distribution is related to the true type distribution via a stochastic matrix, which is actually invertible. This is what we show. And hence, once you estimate the visible type distribution, you sort of like multiply by the inverse of the stochastic matrix to get your true type distribution. Once you have the true type distribution, you can estimate the die-cut value. That sort of is the high-level idea behind the random ordering algorithm. All right, so I will conclude with some open questions here. So first, very interesting open question is like extending this half approximation algorithm to general unbounded degree graphs. Right now, we have results only for bounded degree graphs in the single pass setting. In fact, we actually already have like an order 1 over square root of n pass algorithm, log n space algorithm that achieves half approximation for general graphs. And at a high level, we show that you can actually modify the distributed algorithms in such a way that high degree vertices do not need to receive messages from all their neighbors to determine what their assignment are. We show that it suffices for you to sample just messages from D neighbors in each round. So in that sense, like when you try to simulate a low distributed algorithm with a multipass algorithm, in each round, instead of looking at all your neighbors and what their assignments are, each pass you sort of just sample D random neighbors and try to find what their assignments are and so on. And so this is sort of the modification that we do and show that this is sufficient to get a multipass algorithm. So the challenge is really like trying to implement this algorithm or getting any sort of modification for it in fewer passes, and we don't know how to do it even with a randomly ordered stream. That sort of is the first open problem. Second problem is the more interesting question, where can we extend to other CSPs? Like the previous works that I mentioned for both lower bounds and the upper bounds, the most interesting thing is like trying to understand the approximations for more general CSPs here. Now, the best candidate we have right now is this thing called Max-DICUT, where say this is a CSP where the constraints are just AND constraints, and you want to find the assignment that maximizes the number of constraints you satisfy. So we already know quite a lot about this particular CSP. In this work, we showed that if you look at the little O of n space approximation, that's somewhere between the random assignment, whatever that gets for the CSP, which is like half power k, and half to the power k minus 1. We already showed this part, that this is where your approximation factor lies in little O of n space. And in fact, in a joint work with Boylan, Huang, Prasad, and Singer, we actually gave a closed form expression for this approximation ratio achieved by the bias algorithm, which is the best in little O of square root of n space. And Singer established that, in fact, you have oblivious algorithms. So Max-DICUT, you also have oblivious algorithms for Max-DICUT that beat bias approximation. So he basically showed that you can beat this closed form expression that we got using bias algorithms for Max-DICUT. So now the question is that, can you go all the way to like half to the k minus 1 approximation for Max-DICUT in sublinear space? And interestingly, the smallest open case is even Max-DICUT. Like the distributed algorithm that I described before actually works for all submodular function. I mentioned just Max-DICUT here, but it's actually a distributed algorithm that works for any submodular function. You can get half approximation. But Max-DICUT itself is not submodular. So it's not clear for Max-DICUT if you can get half approximation. And I hope sort of this line of inquiry leads to like newer distributed algorithms for these CSPs that hopefully gets translated also into streaming algorithms. And yeah. Thank you. Thanks a lot for your attention. Thanks.
Any questions for Santhoshini? So for Max-DICUT, what's the best to do in lower bound for half minus epsilon approximation?
Oh, that's a very good question. We don't know any lower bound for half minus epsilon approximation. All we know is just that we cannot beat half approximation in little O of n space, but it's not like we have like this nice, even in terms of passes or something. We have a multipass algorithm now which gets 1 over square root of epsilon passes and half minus epsilon approximation, but we have no idea if the dependence on epsilon is tight or nothing like that. Yeah, that's open too. Yes.
Is there any intuition for the invertible matrix MU?
Yes, there is actually a very nice intuition. I can describe it very quickly. It's a very great question, actually. Okay. So this is the true type. This is the visible type. Great. This is the slide, right? So here's the intuition. What happens is that, so let's say I mean, the number of possible types is only a constant. Imagine like, so I'm trying to write this like stochastic matrix where, let's say, all the columns and the rows are actually like indexed by these types. Now, if you look at the visible type, it has this interesting feature that it can only be a subtype of your true type. Like if your true type is something, what you see is like sort of like some edges are missing, but it's sort of like a subgraph of this true graph. So this matrix is actually like a upper triangular matrix or something, with all the diagonal entries being non-zero. Because if your true type is something with at least some non-zero probability in the stream, as long as these edges arrive in this nice order, like first layer, then second layer, then third layer, you're still going to see the correct type. So the diagonal entries are all non-zero, but it's only like upper triangular or lower triangular. I don't know, depends on how you index it. But you're not going to like, once you have a true type, all the visible types are like subgraphs of the true type. So this is like an upper triangular matrix with diagonal entries non-zero, and so it's immediately invertible for free. That's a very good question. Thanks.
Okay.
Thank you so much. Yeah.
we had budgeted a little bit of time